In probing the limits of what we can measure on the smallest scales, Werner Heisenberg, first considered how well we could measure the position and momentum of an object. Part of the problem is that measuring one position or momentum causes us to lose information about the other. Delta x here is going to represent our uncertainty on the position of a particle's location. Delta p is going to represent our uncertainty on the momentum. Remember that momentum was mass times velocity. We use p to represent momentum. So Heisenberg reasoned that our uncertainty on the position is going to be very similar to the wavelength of light. The wavelength, let's say we're thinking about a photon, the wavelength of the photon. And then that the uncertainty on our momentum is going to be very similar to the Planck constant divided by the wavelength. So doing a little bit of math, which we won't go through here, it involves a little bit of calculus too. He came to the conclusion that the multiplication of your uncertainty on the position and your uncertainty on the momentum must be greater than or equal to the Planck constant divided by 4 pi. So in conclusion, it is impossible to measure the position and momentum of a particle simultaneously with uncertainties that multiply to be less than h over 4 pi. There's always going to be some built-in uncertainty on our measurement of position and our measurement of momentum. And that is the idea of Heisenberg's uncertainty principle, which we are going to apply to solve a problem.
We are going to apply the Heisenberg uncertainty principle. The speed of an electron is measured to be 5 times 10 to the 3 meters per second to an accuracy of 0.003%. Find the minimum uncertainty in determining the position of this electron. To solve this, we have to use the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle says that our uncertainty on the position times our uncertainty on the momentum is greater than or equal to Planck's constant over 4 pi. We want to find the minimum uncertainty on the position, and that's delta x here. So I need to solve this equation for delta x. To do that, I have to divide both sides by delta p here. So divide by delta p. Dividing by this number is the same thing as multiplying by 1 over delta p on this side. So my uncertainty on the position is going to be greater than or equal to Planck constant divided by 4 pi times our uncertainty on the momentum. To figure out delta p, that's my uncertainty on the momentum. This is not the momentum. It's my uncertainty on the momentum. So to figure that out, I have to figure out what is the momentum of my particle and then determine what is my uncertainty on that momentum. All right, so the momentum of my particle, this is an electron, it has mass, so I can use that the momentum is equal to its mass times its velocity. So that's going to equal the mass of my electron. So to remind ourselves that we're dealing with an electron here, the mass of the electron is 9.1 times 10 to the minus 31 kilogram. And we're multiplying it by the speed of it, which is 5 times 10 to the 3 meters per second. So my momentum of the electron is 4.55 times 10 to the minus 27 kilogram time meter over second. Now, the momentum is the mass times the velocity. We know the uncertainty on the velocity. So that's going to tell me that the uncertainty on my momentum is going to be the same as the uncertainty of my velocity. So the uncertainty delta P of the momentum is going to be my momentum times this accuracy to how well I know my speed of the particle. Now, I know my speed of the particle to an accuracy of 0.03%. Okay, we've got to take that from a percent to a decimal, or write it in its decimal form, that percentage. So how do we do that? Well, we remember, when you think about, let's say, an exam. Okay, if you get a 90% on the exam, that's also 0.9 as a fraction. All right. So to take something from a percentage to a fraction, you have to move the decimal 2 spots to the left to get it in its decimal form here for the percentage. So if I have a percentage of 0.003%, I've got to move my decimal 2 spots more to the left to get it to me in its true decimal form as something out of 100. So that would be 0.00003. These are the same thing. Okay. This is my accuracy in the percentage, and this is my accuracy here in the decimal. So I'm going to multiply my momentum by 0.0003. This is the accuracy. Oh, I need an extra 0 there. 4 zeros and a 3. This is the accuracy to how well do I know my momentum. I know my momentum as well as I know the speed. The mass of the electron, we're not going to have any uncertainty on that. So I take 4.55 times 10 to the minus 27 kilogram meter over second and multiply it by 0.00003, and that will give me the uncertainty on my momentum measurement, which is 1.365 times 10 to the minus 31 kilogram meter over second. Okay, that's the uncertainty on my momentum. And that's what I'm going to use right here in my equation for finding the minimum uncertainty here on my position using Heisenberg's uncertainty principle. So for my Planck constant, I am going to use our Planck constant in joules times second. So that's going to be 6.626 times 10 to the minus 34 joules times second. And then I'm going to divide it by 4 pi times the uncertainty on my momentum, which is 1.365 times 10 to the minus 31 kilogram meter over second. All right. And then I'm going to do that calculation. This is 3.86 times 10 to the minus 4 meters. Right. If we wanted to put that, let's say, in millimeters, I can multiply this by 1 meter has 1,000 millimeters. Multiply it by a conversion factor. Those meters cancel here. 3.86 times 10 to the minus 4 meters is the same as 0.384 millimeters. So for this particular problem, we know that the uncertainty on the position of my particle. And the uncertainty will be greater than or equal to 0.384 millimeters. So what the Heisenberg uncertainty principle tells us is the minimum that we can know for the uncertainty. The uncertainty on my particle will never be able to get smaller than this, 0.384 millimeters. That's the best that we can do on the uncertainty of our measurement for the position. It's likely that the uncertainty on my position is going to be greater than 0.384 millimeters, but the uncertainty principle tells us that we could never hope to know the position of this particle better than 0.384 millimeters.
Now, you've probably heard of Schrodinger's cat and superposition. You might have, especially when we were thinking about our physics memes, and you might have encountered this, this on the internet. You might have learned about Schrodinger's cat. Well, we're going to just briefly talk about Schrodinger's cat and something called superposition. Here is a schematic of the Schrodinger's cat experiment. You have a sealed box in which you place a cat, a flask of poison, and a radioactive source. One type of device that can measure radioactive sources is called a Geiger counter. So let's say that we place a Geiger counter inside this box. So if an internal monitor inside the box, a Geiger counter, detects radioactivity, which should be a single atom decaying from one state to another state lower down on the periodic table, which we'll talk about in a future mini lecture. If our Geiger counter detects radioactivity, it is going to shatter this flask of poison, which will release the poison and it will kill the cat. The Copenhagen interpretation of quantum mechanics, which was one school of thought for quantum mechanics early on, implies that after a while, the cat is simultaneously both alive and dead. Yet, when one opens the box, one will discover that the cat is either alive or dead, not both alive and dead. So this poses the question of when exactly quantum superposition ends and reality resolves into one possibility or the other. So quantum superposition, or just superposition, refers to this idea that something could be both true and false at the same time, or something could be both up and down at the same time, or the cat could be both alive and dead at the same time. Superposition is this idea that you could have two or more states of something happening at the same time. But you don't ever know in reality whether that thing was up or down, left or right, alive or dead, until you take the measurement, till you open the box and check to see what's up with the cat. So this is one of the underlying principles of quantum mechanics. And this all has to do with the probability of what do we know about these quantum states. Heisenberg uncertainty principle was thinking about our uncertainty on position and momentum. You can never know the true state of an event until you take a measurement of the event. And once you take the measurement of the event, you find out, and once you take a measurement of the event, then you learn what the outcome of the experiment is. And sometimes, well, I've taken 3 semesters of quantum mechanics, 1 in undergrad and 2 in grad school. And it's this whole idea, we talk about it as collapsing the wave function. We can think about quantum mechanics also by studying what we call the wave function of these fundamental particles. And whenever you take the measurement, you collapse the wave function. You essentially force this state to decide what are the outcomes going to be. And until you force that state to decide by taking the measurement, you could have a bunch of different outcomes with some level of probability. So that is Schrodinger's cat.